Okay, so I hope you all had a great break. Today, we're going to look at chapter 20. Sorry, lecture 20. So this is I think this is a half point. I think in general we're going to have like 38 or 39 lectures. I'm not sure, but we're halfway there. Okay, so maybe a little bit about the schedule for this week and next week. So today we're going to look at a couple more examples about the positive recurrent Markov chain. And on Wednesday and Friday, we'll be looking at branching process. As you guys have noticed, this is like the last problem from our homework about branching process. And I think we'll also be looking at branching process also next Monday. And on Wednesday, we'll do a few more examples of the infinite state space Markov chain. And on Friday, we're going to have our second midterm. It's only going to be about the infinite space Markov chain stuff. Okay. All right. So today is more examples. All right. So first, I guess let us recall the definition of positive recurrent. Right. So this is something that we had seen just last Friday. Sorry, the Friday last lecture. So you say element X inside our state space S, well, we say is just recurrent. If this is one of the definition is T, that the time that we return to X, this is less infinity, given the Markov chain starts at X. This has probability 1, right? This essentially guarantees that this random variable T of X is finite almost surely, right? I'll use a color chalk. So this essentially says this random variable is less infinity almost surely. Right? So this is equivalent with the statement. And then given a random variable that is finite almost surely, then of course we can also look at its expectation, right? So then we just have the following two definitions. So if the expectation of T of X, given X0 is X, this expectation is finite, and we say X is positive recurrent. And on the other hand, the second case, of course, is the same expectation here is infinite. Then we say X is null recurrent. Okay, so let me highlight the important words here. So we have the positive recurrent, null recurrent, right? And then they both fall under the case that it's recurrent. Okay, so the reason we have this idea here is that because when the state space is infinite, there might not exist a stationary distribution, right? As we have seen last Friday. So in general, when the Markov chain, when the infinite space is infinite, if the Markov chain is transient, then there are two cases, right? One is there is no non-zero solution that solves pi is equal to pi times p. The other case is there are non-zero solutions, but we cannot normalize the pi into a probability measure, right? And in the recurrent case, we also have the two cases, right? When the Markov chain is null recurrent, so this is the example that we did for the symmetric random walk on Z. In that case, we do have non-zero solutions pi that solves pi is equal to pi times p, right? Just take pi to be a constant vector. Well, it will be like infinite dimension vector, but just any constant. It satisfies pi is equal to pi times p, but then pi is not a probability measure. It's only in the case when the Markov chain is positive recurrent, then we can obtain a stationary distribution in this case. So this is what we're going to write next. Maybe I'll just call them, instead of calling them theorems, I will just call them some facts. And these facts might also be helpful for your homework. Some facts. You can think about them as theorems. I'll just say them as facts. Right, so first is if X communicates with Y, then X is positive recurrent. If and only if. Okay, I'll just write it out, if and only if. Y is positive recurrent, right? So this says positive recurrent is also a class property, right? So any elements that they communicate with each other, they share this property. So if it's a class property, then we can conclude the following. So given an irreducible Markov chain, right? So we know in irreducible Markov chain, any state communicates with another state. So now we can say whether if the Markov chain is positive recurrent or not, right? So it makes sense. Because by definition, positive recurrent is only defined for elements inside the state space. But if they all communicate with each other, then we can just say whether the Markov chain is positive recurrent or not. So given an irreducible Markov chain, then there exists a unique stationary distribution. Let's call this pi, if and only if the Markov chain is positive recurrent. Right. So this means like if we want to show a Markov chain is positive recurrent, I mean, we can just try to find a stationary distribution. If there exists a stationary distribution, then we can just right away say the Markov chain just has to be on positive recurrent. And also we have furthermore, so pi at x, 1 over expectation. So instead of writing this long way, condition on x0 is x, I'll just use the notation that we all have seen before. I'll just write here, t of x. Right, this means we start our Markov chain. This little x here means we start our Markov chain at little x, right? So we start, this is conditional. X0 is little x here. So this is a little x here. Okay. Yes. Right. Yes, yes. Yeah. And I guess another way to, I guess, to see the uniqueness, essentially, we can also look at this to see the uniqueness, right? I mean, this expectation here is a determinist number. It's fixed. So for any x, pi of x just has to be unique. It has to equal to this 1 over this expectation. But that's another way we can see a uniqueness. All right. So any questions so far? If not, we'll jump into some examples. Right. Okay. So let's see, let's cut the board in half. So the first example we're going to look at, this is called the success run chain. The state space is going to be the non-negative integers. So we have 0, 1, 2, 3, etc. Right? This. And then the chain just goes like the following, right? So with probability p, we're going to jump forward by 1. You know, p. And then with probability 1 minus p, we're going to go back to 0. So of course, I can say at 0 with probably 1 minus p, and then 1 goes to 0 with 1 minus p, and then 2 also goes to 0 with 1 minus p, and a 3 also can go to 0 with 1 minus p, etc. Right? And so to write down the okay. So there's and then the matrix p here is going to look like the following. right? So now it's going to be an infinite matrix. We have 0, 1, 2, 3, da, 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 0, 1, 2, 3, da, da, da. And then the first column, so what's in the first column? Oh, maybe I'll ask you guys. The first column of the matrix P. Yeah, it's all 1 minus P. Okay. Right? And from 0, we go to 1 with probability P. And then we cannot go to 0 go from 0 to any other state. So these are all just 0. Right? And then from 1, we cannot go to 1. So this is 0. But we can from 1, we can go to 2 with the probability P. And we cannot go to 3, etc. and all the other states, right? And then from 2, we cannot go back to 1. We cannot stay at 2, but with probability P, we can go to 3. Right? And then you guys, I'm sure you guys can see a pattern here. So the first columns are all 1 minus P. And we also have this like kind of like upper diagonal of P's right over here. And then the rest of the matrix are just all 0. Right? So this is like a huge 0 here. Okay, so this is going to be what the P looks like. Okay, maybe a motivation for this Markov chain. So you can think about this is a number of baskets made in a row, right? So for example, we shoot free throw, and each time we make the free throw with probability P, and we miss with probably 1 minus P. And then we can look at how many shots that we made in a row. It would follow this Markov chain, right? So you either make the shots, so the count goes up, or you miss one, but the count all the way goes all the way down to 0 because we only count the number of shots that we made in a row. Okay. So in this case, maybe let's just try to find the let's find the stationary distribution. Fine. Stationary. Right. So in this case, finding the stationary distribution, unlike the finite case, often we just solve a linear system. But in this case, there's really no linear system to look at it. So we could just kind of have to like look at the equation and see what kind of relation that we get, and then to solve it this way, right? So, but it's the same equation we're trying to solve, right? So pi in this case is going to be, pi 0, pi 1, pi 2, this infinite vector, and then we're trying to solve pi is equal to pi p. Okay, maybe I'll write the other way around so it's more natural. So maybe pi p. Okay, so now let's just look at so essentially we can just look at the left-hand side and right-hand side and then compare them entry-wise, right? So look at, so inside of pi, so often, so imagine we have a pi here and then we have a matrix P. Okay, I'll write it this way, pi P. Let me fill in the matrix. So this is pi 0, pi 1, etc. And in this matrix here, we have 1 minus P, 1 minus P, etc. And then we have P, etc. And then 0, 0 here, right? So maybe I'll ask you guys. So so what is after this matrix product of pi with P? What's the first entry here? So now it's gonna be like an inner product between this vector here, this horizontal vector, and this vertical vector here, right? So that's gonna be the entry that is over here. So what is this entry? What is the inner product between pi 0, pi 1 with 1 minus P, 1 minus C, 1 minus P? Exactly, right? So from this side, just from looking at the first entry here, this first entry is just given by, pi 0 times 1 minus P. Okay, I'll just write it this way. And then pi 1 times 1 minus P is just summation. I goes from 0 to infinity of pi I times 1 minus P, right? So that's this entry here, just from the product. And on the other hand, we know that this has to be equal to pi 0, right? So this is coming, this pi 0 here comes from the other side of the equation. And this is because it's the first entry here of this product. And on the other hand, the first entry of this vector is pi 0. So we have to have this equality. Okay. So now we see that the 1 minus p here doesn't really change depend on I. So let's just add a bracket here. Another way, I factor out the 1 minus p. So now what is the infinite sum here if pi is a stationary distribution? It's 1, right? So in that case, we solve for, at least we solve for pi 0. If a stationary distribution exists, we know pi 0 has to be 1 minus p, right? Because this is equal to 1. It's 1 because pi is a stationary distribution. So I'll just write here. So we have solved pi 0 is 1 minus p. And then next, we can easily solve for pi 1, pi 2, etc. Just by looking, again, just doing like this kind of analysis where we look at just compare them entry-wise. So I'll do on the other board. Okay, so we have found pi 0 is 1 minus p. Let's try to find pi 1. Right, so let's again look at this product. So we have pi 0, pi 1, etc. with the matrix P. This is 1 minus P, and then we have a P, and then we have P, etc. And the rest are 0. So now let's look at the second entry here. What's the second entry in this product? So it'll be like the inner product of this vector with this vector. So what do we get over here? The second entry of the product. It will be exactly right. It's just pi 0 times p. And what is the second entry is on the other side? What's the second entry of the other side of the equality will be pi 1, right? So now we know pi 1 is equal to 1 minus p times p. So why don't you guys try to find pi 2? I'll give you guys just a minute or so to find pi 2. So maybe I'll highlight. So we have found pi 0, pi 1, and then what's pi 2? And there's a obvious pattern that we can see just after we find pi 2. Okay. Right. So what is pi of 2? Right, yeah, p squared times 1 minus p. I mean, okay, and then I'll say the way we can find this, just look at the next entry, right? So it will be in the product of this vector with this column here, well, right? So the third entry in the product will be equal to the third entry here in this pi, right? So the third entry is in the product is equal to the third entry of pi. The third entry of pi is pi 2. The third entry in the product is going to be p times pi 1, right? P times pi 1 is going to be 1 minus p times p squared, right? So, and then you can see that this way, we can actually just find it, the stationary distribution in this case. So, okay, so in general, then we just have, so we have pi of k is just going to be equal to 1 minus p, and then p to the kth power, right? So we just have this. And what is this distribution? It's a geometric distribution, right? So this is so the stationary distribution in this case just follows k is equal to 0, 1, 2, etc. Right? So indeed we found a stationary distribution, right? And in that case, it would also show that this Markov chain is positive recurrent, because this is the not only to solve the equation. I mean, it's a probability density function. I should say probability mass function for the geometric random variable. So of course they sum up to 1. Right? So is stationary distribution. Any questions about this example? So a lot of the finding the stationary distribution will just be compare these two entry-wise, right? At least this side, because essentially some relation here will already give us the entries here are exactly just the stationary distribution pi 1, pi 2, pi 0, etc. Right? So somehow we can often derive some kind of relation just by looking at them entry-wise. Okay. Any questions? Okay. So let's move on to the next example. As people are still looking at this board. So everything okay? Okay. So the next example is called the renewal chain. And this is not really the renewal process, which we might look at the end of this course. It's just a special Markov chain, so don't confuse this with the renewal process. This is not renewal process. Right. Okay. So the chain is defined in the following way. First, we have to fix a sequence of integers. Let's fix Q. Fix a sequence. Q0, Q1, Q2, etc. Right. And then the easiest way to think about these Qs, just think of them as the probability mass function of certain random variable that takes value on 0, 1, 2, and 3. So the easiest way to think about just think that we have a random variable we have some random variable that's called the z with the probability that z takes the value k is equal to q sub k, right? So it's a problem. These values are just some probability mass function of certain random variable z, right? Which has nothing to do with the Markov chain. You can just think about this as some random value, a random variable z. Okay. So this is we fix a sequence of numbers q0, q1, q2, etc. And then I'll just put this in parentheses, right? Okay. So now I'm going to draw the transition diagram for the chain. So again, it takes value from 0, 1, 2, 3, and okay. So in this case, it stays at 0 with probability q0, and then the chain jumps to 1 with probability q1, and then the chain jumps to 2 with probability q2, and the chain jumps from 3 with probability q3. And then you can already see where this is going, right? And then for coming back, the chain will just always jump back with the probability 1 here. So essentially, you can think about what this chain is. So with some probability, I'll jump to some integer, and then the integer will just keep coming back to, comes back to 0 one step at a time. And it's also helpful to sketch out the general shape of P. Right. So we have 0, 1, 2, 3, 0, 1, 2, 3. Okay. In this case, we stay at 0 with probability Q0. And from 0, we can go to 1 with probability Q1. We go to 2 with probability Q2, and we go to 3 with probability Q3, right? Etc. So that's the first row of the transition matrix. And from 1, we come back to 0 with probability 1. The rest of these are just 0. From 2, we can come back to a 1 with probability 1, right? So because we always come back one step at a time. And then this is 0, 0, 1, 0, 0. Again, just to highlight this matrix, so we have the first row here, which is the Q zeros, and then we have this lower diagonal term, which is sequence of 1 in our transition matrix. Okay. And for now, let's just assume the QKs, they're all positive. So there's no zero values, right? And but don't assume this in your homework, right? So in the homework, I think there is a similar problem. In that case, the QKs can be 0, right? So don't assume that. So for now, maybe we don't have to assume. But I mean, yeah. So let's assume that for now, let's just assume the QKs are all the entries Q are positive, right? So that we work with a irreducible Markov chain. Right? Of course, we don't have all the QKs to be positive to have them. So okay, now yeah. So let's just assume that the QKs to be 0. Right? So the claim that for this Markov chain, the return probability is actually pretty easy to compute. So for any k, for any integer k, that so what's the okay? So the probability of 0. This means just we start the Markov chain at 0, right? What's the probability of the return time is equal to k plus 1? Maybe I'll ask you guys this. Right? So a hint is that it really only depends on the first step, right? I mean, because the rest of the step will just coming back one step at a time. So if we return to 0 in k plus 1 steps, what is this probability? It's a 1, or well, it's not quite 1, right? Because we fixed the k. We know it will always return to 0, but what is the probability that we will return to 0 in exactly k plus 1 steps? Where does the first step have to go? You can think about in order to say the first return is k plus 1 step. Yeah, exactly. The probability is qk, right? And this is because in order for us to return to 0, the first return to 0 is exactly k plus 1 steps. So from 0, we just have to go to k. So this is our first step. And then the second step, third step, will just be returning, right? So these are all the just returning steps. So this is the first step, and this is the k steps. I should say maybe the second step to k plus 1 step, but then their total k step of returning, right? So in general, this just means that in this case, we just have to be equal to qk. I mean, there is a precise way of writing this down, but maybe I'll write this. So this is p0. Given the return time is k plus 1, the sequence just have to behave this way, right? The first step, we just have to go to k. And then the second step, we're at k minus 1, etc. Right? And then until we go to the kth step here, we end up at 0. Right? And from this, we can just use the same trick that we have seen before, just multiplying and dividing by the conditional probabilities, etc. This is exactly can be written as p0k times pk to k minus 1, pk minus 1 to pk minus 2. Maybe I'll just k minus 1, k minus 2, etc. And then this is the first term here is going to be qk, and all these are just 1s. Times 1 times 1. So in the end, it's just going to be qk. Right? And of course, there's also that you can just also think about this intuitively, because the first step just have to go to the integer k in order for us to return to 0 in exactly k plus 1 steps. Right. So now with this, we can already compute the probability that pi 0 is finite, right? So I'll just do it at the bottom of the board. So just from this computation, from this, then we know the probability that we start at 0 of T0 being finite. This just has to be equal to the sum, right? So we can rewrite this T0 return time to 0 less than infinity as a infinite sum of this form, right? So this has to be equal to the summation as I used k, sure. K goes from 0 to infinity of T0 of T0 is k plus 1. Right? This just uses the this is known as the countability additivity of the probability measure. Right? Okay, maybe I'll just write one more step here. I'll just pull this up. Right, because this here is the same thing as P0. And then we have the union as k goes from 0 to infinity that we have the event T0 is equal to k plus 1. Right. Of course, you can also rewrite as k goes from 1 to 0 to infinity, T0 equal to k. But I just want to try to match the calculation above. So I start k at 0, and I use k plus 1 here. Right. And as we have shown that this is the summation, k goes from 0 to infinity of qk, and this is equal to 1. Because qk are probability mass function of certain random variable, right? Well, this means it's finite, right? It's less than infinity. And what this implies that this Markov chain is recurrent, because we have shown this probability here is finite. So let me highlight. We have shown this probability here is finite, right? So by definition, it's a recurrent Markov chain. Yeah, so this Markov chain is recurrent. Right. I used to do less than infinity to show that it is recurrent. Oh, yes. Sorry. It's equal to 1. I was thinking something else. Yeah, you're right. Yeah. It's to show that T0 is less than infinity almost. Right? Yeah. Yeah. So we've shown this probability here is equal to 1. Right. So this is equal to 1. Right. So it is. Thank you. Yeah. So, yeah. What I meant to say is T0 is less than infinity almost already, but then I wrote it. Thank you. Questions? Other questions? Yeah. Yeah. Yes. Yes. Yeah. And okay. And then in this case, this Markov chain will not always be positive recurrent. This is by computation. We'll see this. Okay. On the other hand, for this Markov chain, because everything is fixed, p and 1 minus p, we show that this is always going to be positive recurrent because we by finding the stationary distribution. But for this one, it's not going to be always positive recurrent because we started with the sequence Q0, Q1, Q2. By changing the values of Q's, the Markov chain might not be positive recurrent. It could also be null recurrent. Okay, and now let's see how this happened. And then the way we do this again is going to be try to solve for the stationary distribution. Right, so we solve. When we say we solve, maybe we should really say we try to solve, right? So we don't know whether there exists one or not. We solve for pi of p. Look at the pi, right? And again, we're going to look at this entry-wise. Well, in this case, it's quite simple, right? So there's a really simple formula that we can derive, right? So first, let's look at the product side of this side. The matrix is up there, so we have Q1, Q0, Q1, Q2, etc. And then we have 1 in the lower diagonals, and then these are all 0 here, 0 here. So now let's ask, so suppose we look at the kth entry here. So let's take this vector and this whatever, okay, I'll just do it here. So suppose that this is the kth entry. So what is the kth entry? Can you guys tell us about it? So what is, if we're going to write down the kth entry of this product explicitly, so what would be the kth entry here? Exactly, right? So it'd be qk times pi of 0 plus pi of k plus 1. Right? Because imagine if we're doing this inner product. So the first entry here is pi 0, right? And then the pi 0 will meet with the qk in the first row. And we also have the ones in off diagonal, right? It's lower diagonal. So the pi k plus 1 entry here will meet with entry 1, and then the rest are just 0. So in the inner product, we only have the first term from the inner product and also the k plus 1 term from the inner product. Right? So this is from the product side, and what's the other side? Well, it's the kth entries, it's pi k. So we get this relation. So now we can look for a pattern here from this. I like this. Right. Okay, so should I move to the other board? Okay, I'll just, okay, I think it's enough, right? So first, let's look at pi 0. Right, just by this formula, pi 0 is equal to q pi 0 times q0 plus pi 1. Right? So this is what the formula gives when we plug in k is equal to 0. So we're going to look for a pattern here. And now let's rewrite this in terms of pi 1. So this implies pi 1 is equal to pi 0 times in this case 1 minus q0. And another way to rewrite the 1 minus q0, so just think about, we can rewrite this 1 minus q0 as the probability of our random variable that we started with z that is greater than or equal to 1, right? So these two, they are the same. So let's just rewrite this. Let's rewrite this as pi 1 is equal to pi 0 times the probability that our random variable z is greater than or equal to 1. Again, just recall that the z over here has nothing to do with the Markov chain. It's essentially just used to define the sequence of real numbers, pi 0, pi 1, pi 2. Right? And then 1 minus q0 just means the random variable z can now take the value 0, right? So that's the probability that z is greater than or equal to 1. Okay, so now let me switch the camera. And then let's look for, so over here, we look at pi 0. So now what happens is we look at pi 1. See pi 1. Just from this relation here, pi 1, this is going to go to pi 0 times q1 plus pi 2. Okay. So now in this case, again, let's isolate pi 2. Let's rewrite pi 2. This is going to be equal to pi 1 minus pi 0 times q1. And in this, now let's plug in the value for pi 1. So this pi 1 before, so what I find is pi 0. Now, okay, either one is fine. I'll just write out the first one, times 1 minus q0 minus pi 0 times q1. So now we can factor out the pi 0. So this is pi 0, 1 minus q0 minus q1. Right? And of course, then this is just going to become pi 0 times the probability that our random variable z is greater than or equal to 2. Right? So these are just some patterns that we derive from this relation here. And again, just this notation of using z is not important. You can also just keep a 1 minus q 0. They really just mean the same. Okay. And so in this case, we can see obvious patterns. So we won't prove this in the class, but in general, that we see that the pi of k is going to be given by pi of 0 times the probability p that z is greater than or equal to k. So this is just going to be the general formula for pi of k, which solves this linear system, pi p is equal to pi. So pi k just has to be in that form. Okay. So now, well, in this case, let's see. So what would be the condition that we need in order for it to be in order for this to be finite, right? So because we want the summation as k goes from 0 to infinity of pi k, sorry, to be equal to 1, right? To be equal to 1. And so let's use this notation here. Pi k is equal to this. So this is going to be the sum. K goes from 0 to infinity. And then from the formula, it's going to be pi 0 times the probability that z is greater than or equal to k. So I'll just write okay, I will not write the equal to 1. So I'll just write this way. Right? So from the first line, we go to the second line. And then we can factor out pi 0. K goes from 0 to infinity. The probability p that this is zk greater than k. So maybe I'll ask you guys. So what is this expectation here? I guess this one's slightly tricky, I think. Let me think. Well, yeah, you can take a guess. I don't think it's slightly tricky, but in general, what is the sum? What would the sum look like? What does the sum imply? It's something related with the random variable z. So what does the sum represent? Like, think about, so remember when we're doing the expectation of a random variable, there are two, right? If we have a discrete random variable, so what are the two ways of writing down the expectation of the random variable? So this is one of them, right? Sorry, what? Right. Yeah. So I just mean like in general, we have a random variable. Let's say y. Suppose y is discrete, taking value between 0 to infinity. So one of them is like k goes from 1 to infinity, k times probability p that y is k. Right. Another equivalent way is just writing this as summation k goes from 1 to infinity, the probability p that y is greater than or equal to k. Right? It's just a two-way of writing the expectation of a random variable. This is probably something that you guys have seen before, right, in the probability class, right? I think the proof is just like Fubini. You kind of like rewrite them, but anyways, it's just like another definition, right? It's really a definition of like the expectation. But in this case here, it's slightly tricky because we start at 0 instead of 1. We can just, so in the end, this is just the expectation is actually of a z plus 1. Or maybe I'll just even write it this way. Okay, sure, I'll write z plus 1. Right. And from here, so let's look at some of the conclusions. Well, first is if the expectation of z is finite, then this Markov chain is just going to be positive recurrent, right? Because if the expectation of z is finite, right, but this is just going to be expectation of z plus 1, right? So as long as this part is finite, so we can always normalize it with pi 0. Right? For example, if the sum here is let's say 100, we just let pi 0 to be 1 over 100. In that case, the sum is still equal to 1. So it's still probability measure, right? So we only require this part to be finite. And then we see that in this case, if the expectation of z is finite, then this Markov chain is positive recurrent. And if the expectation of Z is infinite, then this Markov chain is null recurrent. Right? Okay, maybe I'll write it a little more explicitly. Right. So so we have shown that so summation as k goes from 0 to infinity of pi k. We have shown that this is equal to pi 0 times the expectation of Z plus 1. Right. So if the expectation Z is finite, then this Markov chain that has a station distribution. So it is positive recurrent. Right? And on the other hand, if the expectation of Z is infinite, then there is then okay. This Markov chain has then there is no stationary distribution. And this implies that the Markov chain has to be null recurrent, right? Because we have shown that this is a recurrent Markov chain, so it cannot be transient. So it just has to be null recurrent. Okay, so maybe let's see. Yeah, we have one more step. Well, let's just see what happens if we set this to be equal to 1, right? If the summation, okay, maybe I'll just pause here. So is this part okay with everyone? Is this clear so far? Okay, so at last, let's just look at the last part of the computation. What if, let's solve it. If k goes from 0 to infinity of pi k, if this is 1, then this implies that pi 0 times the expectation of Z plus 1 is equal to 1, right? So this means pi 0 has to be equal to 1 over the expectation of Z plus 1, right? Well, this is just because this is the only way to normalize this thing to be 1, right? So we just choose pi 0 in this way. Well, the claims that but just by choosing it this way is actually natural. Okay. So there's a close relation between the expectation of Z and the expectation of T0. Right. So recall that right. So the probability P that we start at 0 of T0 is equal to K plus 1 is equal to QK. This is equal to the probability P that Z is equal to K. Right. So there is a close relation between the random variable Z and T0. So well, essentially you can think about T0, it is going to be, they have the, okay, I'll just write it out. So what this implies is that this recall that we have this equality, then T0 is equal in distribution with Z plus 1. Because this implies that T0 takes the value K plus 1 with probably QK. And of course, Z plus 1 takes the value K plus 1 will also be QK. So they have the same distribution, right? And then if T0 and Z, they have the same distribution, that means how can we rewrite the denominator here? So what is the denominator here? Let's expect. Sorry, what? Right, yeah, exactly. So this is just going to be excitation of T0 that we start at 0. Okay. Yeah. Maybe it's more clear that if I add the plus 1 inside, you know, If z plus 1 and t0, they have the same expectation, then they have, sorry, the same distribution. Now, of course, they have the same expectation. So we derive this formula. So then this formula should look familiar to you, right? Pi of 0 is equal to 1 over expectation of t0, given that we start at 0. It's one of the facts that we have seen. Right? So essentially, just from this, we get this equality. Right? So z plus 1 and t0, they have the same distribution, so their expectations are the same. Well, if this is infinite, then it doesn't really make sense, right? If this expectation here is infinite, it would just be 1 over infinite. Well, you can think about 0, but yeah, but that doesn't really provide us with any information because 0 is always a solution of the equation that we're trying to solve, right? Pi p is equal to pi. 0 is always going to be a solution. So when this expectation here is infinite, it doesn't really provide us with any useful information. Yeah, you can think, yeah. You mean this equation? Sure, yes. Yeah. You can think of, yeah, it will be always that because 0 is always the solution. And if this expectation here is infinite, then we just get the 0 vector. Right. Yeah. It's only it's only useful one that it's finite, or so it gives you something that is between that is positive in that side. Okay. Right. So I think today's example will be very helpful for your homework. Yeah. Okay. And I think that's it for today. And we will be looking at a branching process starting on Wednesday, and maybe we'll come back to more examples. I plan for more examples, maybe for next week, depending on how we do on the branching process. Yeah. So far on the homework, you should be able to do like a number 1, 2, 3, and 4, and the problem 5 is about branching process. I think after Friday's lecture, you should be able to do the homework number 5. Okay, and that's it for today.